Hello class. We're going to talk about section 4.7. It's optimization problems, okay? So what it means by optimization, we're trying to find the most optimal way of doing something, okay? This means either finding the maximum of something or finding the minimum of something. So what we're going to do in this section is we're going to use the material that we learned in the previous sections, such as finding the critical numbers, first derivative test, second derivative test, to find minimums and maximums to optimize the problems that we will have. Now, we're going through a very small set of problems on in this section. You could take an entire class on optimization problems. In fact, when I was in grad school, I took a class on optimization methods in operations research, where we learned a bunch of mathematical techniques to optimize problems. Now, in those, I had to take derivatives, second derivatives, whatnot. Here, it's not going to be as intense as there, but that's the idea. You're going to take a derivative, or maybe even a second derivative, find the critical numbers, and then use the first or second derivative test. That's how all of these problems are. Now, the hard part in doing that is setting up the problem, okay? And in the section, they have steps for solving these problems. Now, the first thing they talk about is understanding the problem. What that means is read the problem, reread it, read it as many times as you have to until you understand what's going on, the information that's told to you, what you know and what you don't know. And then after you've done that, you should draw a diagram. Sometimes the book gives you the diagrams, which is really nice when they do. You don't have to make one up. But if they don't, go ahead and draw a picture, okay? This will help you with the next step, which is introduce notation. Label things in your picture. After you're done labeling them, this is going to help you do the next step, which is express the problem as a function using the notation in step 3. Now, like I said, this is the hard part of the problem. Accurately drawing the diagram, properly introducing notation, and then expressing the problem as a function using your notation. Now, if you could do all of that, in my opinion, that is the hard part. You're on to the easy part now, which is take a derivative, find the critical numbers, use first or second derivative test. Okay? So let's go through a problem. The problem says a farmer wants to fence in an area, so they tell us the area. A is equal to 1.5 million feet squared. And then divide, in a rectangular field, and then divide it in half with a fence parallel to one of the sides of the rectangle. How can he do this so to minimize the cost of the fence? Now, if you think of buying a fence, the cost of the fence is going to be the same no matter what. Doesn't matter how much fence you buy, the cost is going to remain constant, okay? So, the cost of the fence, the price of the materials, and the total cost is only dependent on how much fence you buy. So to minimize the cost, we need to minimize the amount of fence we buy. Okay? So that's what the problem is telling us. Find the minimum amount of fence we need to purchase, or that we need to build this rectangular pen out of, to minimize the cost. Okay? So, let's go ahead and read it one more time. A farmer wants to fence in an area of 1.5 million square feet. So since they gave us the area, we're probably going to have to use the area formula somewhere, and then they say in a rectangle. So the area of a rectangle, first let me draw a rectangle. There's my fence. The area of this rectangle. Let me get some colors. Let's call that side Y. Let's call that side Y. And then let's call that side and that side x, okay? So if you recall the area formula of a rectangle, it's just the length times the width. So xy must equal 1.5. I'm not going to tack on the units right now. So they told us the area, and now we've got a formula for the area based on the picture that we drew, okay? I'm introducing notation. I'm calling the width y. I'm calling the length x. Now let's keep reading the problem. Now it says he wants to make this rectangular field and then divide it in half with a fence parallel to one of the sides of the rectangle. Now, it doesn't matter what side of the rectangle you pick. You could draw it this way, horizontally, because that's parallel to these two. Or you could draw it vertically, then it's parallel to these two. I'm going to draw it vertically. The length of this should also be the length of this, right? So I'm going to label this x. So now we've accomplished what the farmer wants to do. We've got a rectangular field, and it's divided in half, where it's parallel, okay? Where this fence is parallel to one of the sides. Now, when I buy this fence, they're going to charge me per foot, okay? So if I want to find the cost of this fence, it's going to be how much fence I purchase. Of course, times the price per fence, but we are not given the price, so we're leaving that out right now. But the cost is going to be this side plus this side plus this side, which is 3x. This side plus this side, which is plus 2y. Now, we no longer need the picture. We have all the information we need to solve this problem. But now, if you look at our cost function, we want to minimize the cost. So we've got a function of x and y. When we were learning how to find minimums and maximums, we never did this with implicit differentiation. We only did this with functions of x, functions of one variable, in section 4.1 and 4.3. So we cannot find the minimum of this. We need to convert it into a function of x, okay? How we're going to do that is we've got another equation that we can use. What I'm going to do is I'm going to solve for y. If I just divide both sides by x, I get y is equal to 1.5 divided by x. I'm going to take this, I'm going to plug it in right there. So now my cost function is a function of x and only x, because this is 3x plus 2 times 1.5 divided by x. Which we could simplify it a little further. I'm not going to write another line. 2 times 1.5 is 3. So we get 3 divided by x. Okay, now if we want to find the minimum, we need to find the critical numbers and then use the first or second derivative test. Okay? The setup of the problem is done. Like I said, in my opinion, this is the hard part, getting this function right here. Now the easy part is taking the derivative, setting it equal to 0, and I've already said all this before, but let's go ahead and do that. Derivative of 3x is just 3. Ooh, not a plus. Derivative of 3 over x. If you rewrite x to x to the negative first power and apply the power rule, it's going to be minus 3 divided by x squared. Now what I'm going to do, I'm going to take this, set it equal to 0, and solve. Well, since this only has one denominator, there's no denominator over here, what I can do is multiply both sides by x squared, and then distribute this. You get 3x squared minus 3 is equal to 0. 3 paired with the x squared. And then when I distribute this x squared to this piece, the x squared down here and the x squared cancel, just leaving a 3. So I could factor out a 3. I get x squared minus 1 equals 0. And then this factors. X minus 1, x plus 1. So we get x equals 1 here, equals 0, x equals negative 1 here. So we found our critical numbers. We have a critical number at 1, and we have a critical number at negative 1. Now let's talk about these critical numbers for a moment. We're not going to use one of them. Let's think why. Which one do you think we're not going to use? And think of a reason why we're not going to use it. The one that we're not going to use is the negative 1. The reason being is we are building a fence. X is the length of a side of the fence. We can't have a negative length, so we're going to throw this critical number out. So, not going to use it. Let's see, I'm going to get rid of this. I'm going to get rid of this arrow. Critical number, x equals 1, and then this is in millions of feet, okay? Millions of feet because our area is millions of feet squared. Areas are always the units squared. The normal lengths are just the not squared units, so just feet. So what we can do is just take this. We've got a nice function for y, don't we? We can go ahead and plug it in. Y is equal to 1.5 over 1, which is 1.5 million feet. Okay, so we found the dimensions of the pen and the fence in the middle that will ensure that we have the minimum cost. Not only that our area is 1.5 million feet. Notice if you take 1 times 1.5, you do get 1.5 million feet. Now, we only got one critical number in this case. So, based on the problem, they want us to find a minimum. We can infer that this has to be where the minimum occurs, okay? But let's go ahead and apply the first or second derivative test to just make sure that it is a minimum. Now, me personally, I want to do the second derivative test, and that's what I'm going to do here. You could use the first derivative test. I think the first derivative test is a little more work. In this case, using the second derivative test, taking the second derivatives, or derivative of this one, is very easy. C double prime of x is equal to, well, the derivative of 3 is 0, goes away. Rewrite this with a negative exponent to the negative 2 and apply the power rule. The negative 2 comes out front. You got a negative times a negative, which is a positive. You'll have a 2 times a 3, which is a 6. And then you drop 1 power. You're at a negative 2. When you drop 1 power, you're going to go to a negative 3. So the second derivative is equal to 6 over x cubed. Now, to apply the second derivative test, we have to plug in our critical numbers. In this case, it's only one critical number. So, C double prime of 1 is greater than 0. Based on the second derivative test, we know that there is a local min here. This is just the outcome of the second derivative test. If you plug in your critical numbers and the second derivative at that critical number is greater than 0, then it's a local minimum. I told you guys how I remember it. Since it's greater than 0, it opens upward. Upward is the positive direction. Since I gotta draw it like this, I've got a minimum, okay? If it was negative, it'd be downward. I have a maximum. So now I know for sure that this is a local minimum, and this y has to be a minimum as well because that one was a minimum. So the farmer can accomplish this, can minimize the cost. Let's just draw our picture one more time. If y is equal to 1.5, x is equal to 1, x is equal to 1, x is equal to 1, and down here, y is equal to 1.5. This right here will minimize the cost of the function, okay?